For the last lesson of the chapter, we're going to talk about infinite geometric series, like the following one. A very simple one that we've talked about a few times in class already. 1/2 plus 1/4 plus 1/8 plus 1/16. Powers of 2 in the denominator, and it's going to continue forever. We even said in class that we could express this in sigma notation by saying the sum from n equals 1. And if we look at the denominator, we can actually set the progress, or we can just talk about the entire sequence as a whole of having an r value of 1/2 and a t of 1 of a 1/2. So what we'd say is 1/2 times 1/2 to the n minus 1. But then our upper limit for an infinite geometric series would be infinity. So this is the series that we're summing, written out in sigma notation. This is written out kind of in expanded notation. And both of these have the effect of having sums that start to approach a number. If I do the sum of the first one, it would be 1/2, but the sum of the first two is 1/2 plus 1/4, which is 7/8. Sorry, 3/4, not 7/8. The next one is 7/8. If I do s of 3, which is taking the previous one, 1/2 plus 1/4, and then adding 1/8, I have 3/4 plus 1/8, which is 7/8. S of 4, you can start to look at the pattern here, is 15/16. S of 5 is 31/32. And I could continue all the way even to something like S of 10, which would be the power of 10 in the denominator. 2 to the 10th is 10^24, and 1 less than that in the numerator. Now, let's compare the fraction of 1/2 to 1/23/1/24. Think of if you had, like, two of the most important things in the world and you missed one of them, versus if you had 1,024 things and you missed one of them. This fraction here is a lot closer to the number 1. I should say closer to 1 than 1/2 is. And if we start expanding that even further, if I could do S of 11, I would have 2,047 over 2,048. That's getting it even closer and closer to 1. So we know a few things. I know that for this sequence, S of n is always less than 1. Just barely. But I also know as n gets larger, one-half to the n power gets smaller. Well, why does that matter? Well, I should not put an s on larger. Well, if I look back at the sigma notation, I have 1/2 to the n minus 1. As that n gets ridiculously large, that 1/2 to the n minus 1 gets ridiculously small. I could say, in fact, as n approaches infinity, 1/2 to the n power approaches 0. And it stops having an effect at all in terms of the summation. So your terms basically become 0 as you get really, really large. So the sum, S of n, basically becomes something very, 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 very close, like we say, close to the number 1. We could say the sum is 1. And instead of using an n, I'm going to use an infinity symbol to imply that we're talking about an infinitely large series. We kind of did this when we talked about, on one end we have, I think we did a mouse, and this mouse starts at 0, and it's going to start to kind of walk toward 1, and if it walks half the distance in the first trip, and then 1/4 the distance in the next trip, and then 1/8 the distance in the next trip, and let's see how many of these I can actually do before I get really, really, really small. We go 1/16 in the next trip, and that would go 1/32, and then 1/64, and 1/128. And if I add all of these up, it's at, if you can reason that this is never ever ever going to hit that wall. It's just going to get closer and closer, and those fractions are going to get closer and closer. And if I add all of them up and take that last leap of what would it be like to add infinitely many, I'm going to get the entire distance, the number 1. S infinity is equal to 1. So a couple of conditions, but before we do that, let's kind of roll this series up again. 1/2 plus 1/4 plus 1/8 plus ... This series converges. Converges, what it means is that when you add up infinitely many terms, you have a sum. And that's important. This series converges. This series has an r value equal to 1/2. And so what we need in order to have an infinite series that converges is we need the r value to make the numbers smaller. And when I say smaller, I don't mean more negative. I mean smaller as in smaller in their absolute value. In fact, the only r values that are going to make those are going to be r values that are less than 1. Or what I should say is absolute value of r is less than 1. In other words, -1 is less than r, which is less than 1. Or r is between -1 and 1, where r is not equal to 0. So that's really what it comes down to, is we actually absolutely have to have an absolute value of r that gives us something that makes the number smaller. So we're going to kind of do a definition here. An infinite geometric series sorry, it's late and I cannot write well. But an infinite geometric series, one with an absolute value of r less than 1, where r is not equal to 0, because that would give us a trivial example where you just add up all zeros. Absolute value of r equal less than 1, r is not equal to 0, with infinitely many terms. So, kind of important there, and let's do kind of one example here. Let's take (8 minus 4 plus 2 minus 1 plus ... This is similar to the one we did before. We have an r value, though, that's equal to -1/2. So rather than the numbers getting smaller, what's happening is that they get smaller and then smaller and then smaller and smaller, and it kind of starts to look a little bit like this, where we sort of have this wave, but it's still converging. It's still approaching a number. So let's figure out what the sum would be. Well, in order to do that, we need a new formula. We can't just keep guessing all the time. So we're going to take our S of n formula. S of n equals equal to t of 1 times 1 minus r to the n over 1 minus r. And when we talk about very, very, very large n, for large n, r to the n approaches 0. Because when we talk about r, we have an r value that's it's a fraction less than 1. So what that effectively does is it takes this and it cuts it out of the picture. And so my new formula, S of infinity, is just equal to t of 1 over 1 minus r. It's a simple formula. This is formula number 5. So if I kind of star this formula as one to remember, put a little highlight on it, and then kind of carry this back over, I'm going to say S of infinity is equal to t of 1 over 1 minus -1/2, which is 8 over 3/2, or 16/3. And that's what the sum of this infinite series would be. Okay, let's do example number 2. 8 plus 12 plus 18 plus 27. Well, if I do my s of infinity equation, I get t of 1 over 1 minus, and my r value is 12/8, which would be equal to 3 over 2. So 1 minus 3 over 2. If I get that, I get 8 over 1 minus 3 over 2 is negative 1/2, or negative 16. But wait a minute, that doesn't make any sense. How can 8 plus 12 plus 18 plus 27 give us a negative number? What's wrong with this picture? What's wrong with this picture is that it violated our first condition. This r value right here is in fact greater than 1, which means that there is no sum. So this whole thing cancels out, and we have to say is no sum because we have an r value is greater than 1. I could even just say absolute value of r is greater than 1. So what we kind of can state here is that this series diverges. In order to have a sum, an infinite geometric series must have absolute value of r less than 1. That is an absolute must in order to have a sum. So mark that in your brains. That's usually the trick if you can't get something. Okay, we're going to shift gears here. I'm going to try another example. I'm going to write 0.13131313 dot 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 as a fraction. I'm going to do this using an infinite geometric series. So what I get is, let's take 0.13 plus 0.0013 plus 0.000013 plus dot dot dot, and we're going to add that up infinitely many times. Well, what do I get for my r value? My r would have to move this decimal place left 3 places. So that means my r value is equal to well, I don't like that. I was just going to say 1/100th because I prefer fractions, but then we're going to convert it to a decimal just because we're dealing with entirely decimal representations here. So we got an r value of 0.01, and I'm going to do the s equation. We're going to say s infinity is equal to t of 1 over 1 minus r, which is 0.13 over 0.99, or 13/99. We're going to try another one. Let's go prove 0.9 repeating is equal to 1. This is for you, William. If I'm going to prove that 0.9 repeating is equal to 1, let's take that as 0.9999999 dot 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 dot. And I'm going to say that that is equal to 0.9 plus 0.09 plus 0.009 with an r value equal to 1/10, and s infinity equal to t of 1 over 1 minus 1/10, which is 0.9 over 0.9, or 1. That 1 happens to be the decimal representation of 0.9 repeating. Let's go back to another example. Let's go number 5. I'm going to find the sum from n is equal to 1 to infinity of 4 times 5/4 to the n minus 1. Well, again, I could look at this from two perspectives. I can say that this formula says t of 1 is 4 and r is equal to 5/4. If r is equal to 5/4, that means that r, absolute value of r, is greater than 1, which means right away that there is no sum. Or I could list the first several terms and start to see that that's happening. My first several terms for this would be 4 then I would have, let's see, you'd have 4, then you'd have 5, then you'd have 25 fourths, etc. I should put pluses between those, but that's okay. So there's no sum. Let's do another example. Let's go the sum of an infinite series is 125. R is equal to 0.4. Find the first three terms. Okay, well, if the sum is 125, I'm just going to start plugging this into the equation. S infinity is equal to t of 1 over 1 minus r, and solve for t of 1. So S infinity is 125, t of 1 is unknown, and 1 minus 2/5 is 3/5. So if I do a multiply both sides by, let's multiply both sides by 3/5, I get, let's see, 3 times 25, or 75, and I know that t of 1 is equal to 75. Again, that was from multiplying both sides by 3/5. I can show that like this. So t of 1 is 75. Now, r value, we said r was 2/5, so I have to do 2/5 times 75. It's 30. So 30 is equal to t2. And 2/5 of 30 is 12, so 12 is equal to t3. So that's one example that we could do. Let's do another one of those. Let's say number 7. If I say the first term is -7, and the sum is, let's do 200. Let's see if this happens. So I have 200 is equal to t of 1 is -7 over 1 minus r. And I'm going to do 200 minus 200r is equal to -7, or let's see, -200r is equal to -207, or r is equal to 207 over 200. Notice how I didn't ask a question here. That's kind of weird. But I ended up with an r value of 207 over 200, and that r value is greater than 1. So if a first term is -7 and the sum is 200, this right here is not possible. And right here is a proof that it is not possible. If we demonstrate we have an r value greater than 1, then I can write a statement, because the r value is greater than 1, this sequence is not possible. So that could be an instance of why this is proved to be possible. So other than that, I would say I've got enough examples, and that's it.